Hey folks, how's everybody doing today? Happy Wednesday. Hope you're having a good one. Alrighty, let's give that a pause here. Got a couple things on tap today. First, it is July 21st. Oh my goodness, we are in week 11 out of 15 for the course. Just plowing our way through with no breaks over this summer because reasons. And this summer has been not ideal, but hopefully it's going for you folks. I've gotten through some of the quizzes. I've not got them all done for you. So if you weren't hanging out in the Discord chat today, you might have seen that the midterm originally was going to be on 7/14 for 4 hours, and then I didn't have everything in for you. So I said, oh, let's just take the whole week for it then. And I still don't have the quizzes for you. When I was out at the Jellystone camp in Kentucky, their Wi-Fi was awful, just awful. So I was doing everything off my phone hotspot, which was literally better than their Wi-Fi. And that did, got some things done, but was not great. But they're still not in, so I said, if you want to take more time on it, go for it. Because I screwed up, that's my fault, you guys should get the extra time on it. And someone said, well, I already turned it in. So I said, okay, well, I'll turn on 2 submissions. So I'll be getting your quizzes in. So if you want to see those first before you submit your final submission for the midterm, go for it. Yeah, it was bad, Dusty. And the grading, a lot of it is D2L's fault as well, because what I usually do is I grade question by question, and when you have decent internet, that's fine. Like, it says, here's question 1, here's the first submission for it. I give it a score, I click next. Here's the next person's answer for it. Here's the next person's answer for it, so I can grade all of them. But every time I hit next, it has to reload the page. It doesn't, like, bring up all 20 submissions for the quiz, and so I can just go through on a single load of the page. I have to reload it, and that would take forever. So I could go through each person's quiz and grade all 10 questions each time on a single page, and then load the next person's. But that, for reasons, it takes me longer than as I'm like switching through the right and the wrong, those sort of things. So it just took way longer than it usually does, and it was awful. And then I'm sorry. It's been a summer. We are getting close to the end of the pandemic. Thank you, folks, for getting your vaccination. We're getting better numbers in Michigan. I think we're ahead of the statewide average, aren't we? So Michigan vaccination rate versus U.S. rate or something. What is our vaccine tracker? Here we go. Track by state. This is what we want here, right? One sec. I forgot to close my office door. All right, sorry about that. That ought to help a little bit. Okay, so 57% have at least gotten 1 dose, 49% only got 2. And we have by state here somewhere, right? Here we go. By state, Michigan. Okay, so we're barely. No, we're behind. I thought we were ahead. Okay, no, we are behind. That sucks. That's bad news, Bears. But we're getting there. Wow. Mississippi, are they the worst? 33%? That is terrible. Even Alaska, the land of libertarianism, is ahead of Mississippi. Anyway, so we are working on getting towards back to normal. I've got 5/8 of my crew fully vaccinated. My younger 3 aren't eligible yet. Yeah, they'll just take the first one, Dusty, for sure. For sure. All right, so we'll get that in. Take your time. Again, I'm sorry. I don't want that to be a penalty on you folks at all because I'm running behind. So take your time. We're good. The only downside now is that we're running into final project time. But I'm hoping you've already done those long answer questions, and just going through your quiz questions for last minute review will be quick. So I don't want that to take up a lot of time because the final project will hopefully be very interesting if you're into the sort of thing we're going to be doing. It should be a lot of fun. And then yesterday was fun. I had been planning on getting a tattoo right around when the pandemic started, and it never happened. And we're going out places and this or that. And around my birthday in April, before my birthday in April, I was like, hey, I should get it for my birthday. Turns out everyone had been waiting to get one, and I couldn't get booked until July. So I finally yesterday got it, but I've got this vasovagal reflex. Like I used to, every time I get shots or see blood, I'd pass out. And I thought I was getting better with my blood draws. I'd have to do like every 3 months for being diabetic, but apparently not. So I passed out twice while they were doing this tattoo. Ended up throwing up a little bit. The sweet lady doing my tattoo was like, "Oh no, it happens. It's no big deal." As you know, sure. So we got it done. Turned out pretty nice. I'm pretty happy with it. I posted a picture in the Discord, but you can also kind of see it here. If I can turn right hand, turn that way. It's hard to, how do I point this at my webcam here? No, the angle's all off, but that's okay. So it's, the picture in the Discord is better, but it's healing nice. That's right, rebooting, not passing out. Yeah, I just had to reboot twice. So we got Project 4 was due tonight. I think I only had a couple questions on it. I believe I answered everybody. I don't think I left anybody hanging there. So we can talk about Project 4. That was our last individual project. And I'm assuming your self-assessments were good. So we're going to assume that the score you gave yourself is going to be the score you earned. And we should be in good shape for those. I'll be getting those in. I wanted to get your quizzes and midterms in. I'll get the projects in. And we'll have a couple more chapter quizzes to wrap up. But then the final project is the big portion of the grade here. And for groups of 3, so ideally, these are done in pairs, and usually I require pairs when we're in-person learning. Given this remote pandemic stuff and it just sucks, I'm not going to require pairs. I'll recommend it. But if you want to do a group of 3, that'll be an option for you, but your group will be doing more work. For individuals versus pairs, it's essentially the same amount of work, because when you work in pairs, you have to do some additional collaboration and coordination, and the back and forth sort of thing kind of evens that out typically. But if you have 3 people, then you're going to have some additional objectives you'll need to meet. And we're going to present on 8/18. We're going to get together on Zoom, where we can all take turns screen sharing. You'll present your individual or pair or trio project. You can nominate someone from the group or draw straws, however you want to do that. You'll present, or you can all take turns presenting different parts, however you want to do it. And what's cool is when we do that, I'm going to take the rubric and say, okay, show me this part, show me this part, show me this part, and I'll be able to score it live. Believe it or not, you will have a score before the night is up for one thing in the course. Apologies for everything else being awful. It's been what it is. Yeah, we'll be talking about that tonight, Dusty. Yep, we'll be talking about that tonight, what the final project is. So I'm looking forward to it. I think it should be pretty interesting. We should have a lot of fun with it, I think, if you're into that sort of thing. And if you're not, then okay, you might not be quite a fan. But it should be fun. So my thoughts were, we'll talk about Project 4 first, we'll talk about the new material, and then we'll talk about the final project. We can really do them in any order. I'm not too concerned which directions we take those in, but we can do them in any order. But usually I do the project solution first, and then the new stuff, and then the next project. So we're going to use hashing will probably be the most useful as you look at our different data structures, because hashing is just phenomenal, as you'll see when we get to that here. Okay, so we are almost done with new content. We're going to get searching, dictionaries, and hashing. Hashing's not in chapter 23. I think I screwed up the names here for the category. So 23 through 25 is trees, binary search trees, and then heaps. We've actually done a heap when we did our priority queue, the heap structure as a tree, which is cool. We'll look at balanced search trees, and then graphs, and that'll round out the content for the course. Believe it or not, we'll have done pretty much 29 chapters as we whip through these chapters in the text. We go through a lot of material and data structures, which is fun. And then 8/11 I have set aside just to work on the final project. Usually we'd be in person, and I could just kind of walk around the groups and help out anywhere you folks get stuck. So I have no lecture time planned there. So 3 more nights of me lecturing, a night for you folks to work on the project, and then presentations where I shut up and you guys talk. Should be fun. That's sort of the plan. All right. We good to get going then? Let's talk about Project 4 first. So we've gotten less submissions as things have gone on, which is a little concerning. I know a couple of people have dropped, but I'll have to look at how many we officially have left in a second. Oh, and that's the other thing. The college has fall registration happening. I know data structures is typically one of the last courses that you take but fall registration is underway. See, we have officially 19 people registered, so I was expecting more than 13 submissions for some of these things. But, okay, sure. Yeah, so don't forget, fall registration is happening. So if you want to take a look for any other CIS courses you may or may not be interested in taking, that's upcoming here. So yours truly, I'm only doing 1,500 and 2454. So if you've not taken web systems development, I'll be teaching that one. PHP and Java. It's a lot of fun. That's a pretty interesting course. Other classes, we now have Mr. Nasser has joined the ranks of the full-time faculty members, which is awesome. We're back to 4 full-time faculty members at the Orchard Ridge campus, which specializes in the software engineering program. Secure programming. Yeah, that one is typically Mr. Othman. Dr. Othman is fantastic. He is super smart, real great guy, out at the Auburn Hills campus for secure programming. Talk with him about it. So, yeah, we'll see. But that's part of the security track, typically. But that one looks really interesting. I've not taught that one before, but this is more about when we design software, how we analyze risk, understand points of attack, how we can mitigate those sorts of attacks here, which is unfortunately not taught often enough. I wish we had time in our software engineering program to do this work, because it's super important to understand how do I build software that's not easily exploitable. Yeah, there's a list here. What is it called? The top 10 software security risks. OWASP. That's right. It's OWASP. The OWASP top 10. Top 10 here. They've been doing this for years and years and years now, of top 10 security risks, specifically around web application security. And they're still the top 10. They've been doing this for years. The 2017 version was the last one they looked at here. Ways that software is at risk. So I don't actually know, but I believe this will probably be one of the topics. I can talk with Dr. Othman to see. But yeah, this is, we've known these are risks for a long time, and we still just do them. Yeah, injection, all sorts of SQL injection still happens. That's why we use frameworks that protect against this sort of thing. Authentication is hard, sadly. So, right, use the framework authentication is generally pretty good here. Bad APIs, you see in the news all sorts of unprotected API issues all the time. Broken access controls, we did it wrong. Some misconfigurations on our security. Cross-site scripting, we're vulnerable to. Deserialization, this one's interesting. We screw things up when we serialize as possible. Known vulnerabilities, this one is huge. Our new latest and greatest attacks, supply chain attacks, where someone attacks one of your downstream components, or I'm sorry, upstream components that you're just using in your project is huge. Can be issues. Logging and monitoring, you might not even know if you were attacked, depending on what you log and what you monitor. So this is all super important stuff. Was really interesting. I worked on a lot of this previously in my bachelor's program. We spent a lot of time looking at software security and software risks because it was an interesting thing. And this is big. It's a big focus for a lot of organizations. So that's a fun one. Yeah, so yeah, take a look at enrollment. If you've got any other classes to knock out here, fall enrollment is open, and we can go from there. Yeah, so Mr. Nasser is doing C++. If you haven't taught if you haven't taken C++ yet, that's typically in our software track. All right, anyway, we're getting off track here. So we are looking at Project 4. We're doing our little simulator here for seeing how efficient our cafeteria line is if we allow nurses at the front of the line, the doctors, and everyone else has to go behind them, because we want the clinical stuff that the hospital is able to bill for to be done by our clinicians first, right? Because obviously we need to be able to bill for these procedures that they're working on. Because that's the important focus of any good healthcare system, I'm sure, is making sure we take care of the things we can make money on. All right, let's just be honest. Let me fire up NetBeans here. We're going to use a priority queue to do this. We need a class that represents the people in line that could also track their waiting time, so we can figure out what their waiting time is here. And we'll stick them in a little simulator, put them in a priority queue, let them jump their line. We'll have a nurse line, we'll have the doctor line, we'll have the everyone else line. We'll make sure the nurse's line is empty first when we call people up to the order. Then we'll make sure the doctor's line is empty next, and then we'll have everyone else. That's sort of imagining how that might work. Not exactly the case, but that's essentially our priority queue, right? We'd say, instead of just say single line, it's like the fast pass line when you go to Cedar Point or Disney, right? Clear this one out. Right, so here's our little teller station with the screen with all the little like food icons here that they get to click. We got our teller manning this one here, and then we have 3 lines, essentially. We have, this is the nurse line, this is the doctor line, this is everybody else or other line here. So they all get in line here. And then when the nurse, when the teller's ready to take someone's order, he'll say, hey, Mr. Nurse, you come up and take your order. We'll take them out of the queue. Right? If this line is empty, then we can go say, hey, Mrs. Doctor, you can come up here. Go for it. You can take your order. We'll do your order, and then you go through the cafeteria, right? And they take your money, this sort of thing. Right? And everyone else just kind of piles up and waits until there's no doctors or nurses. All right, so I'm going to close these down here. Let's start up a new project. In 2353, there we go. This is project 4. And remember, to do this, we need a class that implements the comparable interface. So we're going to add a class here for employee. I guess just person, right? I don't know. Well, this will just be person. Why not? And then person then will implement comparable of type person. Implements comparable. And then it's going to tell us, no, you don't. Oh, yeah, yes, we do. We want to implement. So when we compare to another person, the other person, well, how do we do this here? Sure. So person, again, I like just calling them other instead here. So person then will probably have a type. So maybe we even have a enum for type. So we might have a public enum type here. How do we do this? This was a list, right, where we'd have nurse, doctor, nope, nurse, doctor, and other, something like that. Ought to be close, right? What are we doing wrong here? Enum type. Let me just Google it. Enum. How do we do these here? Never remember the syntax. Public enum. Okay, there's no equal sign. There we go. Great. When you make a person, then we're going to have a private type here. And our constructor then, person, will want a type enum. So when you create an instance of person, you need to tell me what your type is. So my this type will equal the type. Great. And then we're also going to have a private int for wait time. Or I don't know, a time entered the line. I don't know, time entered line. And a private int for time ordered. And, you know, time as integers is kind of ugly, but it'll be okay. We're not going to worry too much about it here. Private int time ordered, because we need to track here, right? Where we go here? How long they wait, right? Once they get their sandwich, track the time that they received it. So time received order. So time order was received. We're checking when they entered the line and when they received their order. And then their order then is going to be a random something here. And we can figure this out once they get their sandwich, right? So we'll take them out of the line, out of the priority queue, get their order, figure out 1 minute plus the minute per topping, generate the random number for the toppings, and then they get their sandwich at this Subway-style restaurant, which is horribly slow, but apparently it's popular and they're still in business. Time they receive it. We'll do 120 rounds of this. We'll see what the average time is. Okay. Calculate the amount of time someone needs to wait. So we'll need to figure out the average time for people to see what it is. Right. So You're getting points for our worker class that's comparable, nurses, doctors, and everyone else. I went person. I guess we can go worker. Priority queue, when they enter, you time loop to track, a third of a chance a new worker enters the queue. Once the sandwich is done, remove them from the queue, get the next person's order. So this turns out being a little bit rough because you want to, like, we're taking the first person out to get their order. So if someone is ordering, we're not going to say that the nurse gets to jump in front because they're already mid-order. Either way you did it was okay. This one is harder if you take them out when they're done. Really, you want to, like, do their order, work with them, and then we take them out. So I think this was a little bit wrong here in the rubric. I apologize for that. We'll run it for the time. Let's see the average wait time for each worker type. So we'll have their time they entered the line, the time the order was received, and then we need gets for those, right? So then, okay, so to compare to, there we go. So nurses will be the first here. So we'll say they're the essentially we can compare the enums here. Remember, because enums have ordinals, so we're going to return type.ordinal minus the other .type.ordinal. So if they're the same nurses, they're the 0. They're going to be equivalent. If the nurse is 1 and the doctor is the other, right, the ordinal will be 0, minus 1 is the other. And we're going to say, hey, we're greater. Right? Let's see if this works for us. I think this ought to do it here. So my ordinal minus their ordinal. And if they are other, then I'll still be greater. Right? So I should have the greatest priority. Doctor minus a nurse. So 1 minus 0. Here, if I'm a doctor minus the 0 ordinal nurse, then I'll be giving you a positive number. Nurse minus a doctor, so 0 minus 1 is negative, so 0 I have the highest. So negative is typically usually like a min and q. We'll have the highest priority. I think this ought to work for us here. So we need to make a priority queue to put all the workers in. We need a priority queue. Here's our queue, the new priority queue, and this will be of type person, right? Type person. Great, so now we have a place to stick these people here, right? And we're going to do our time loop. Okay, length of the string with nurse is 5 letters, doctor 6, and other? What did you do for other then, Ray? I mean, we did like the long strings that were comparable, so I guess that was easy to compare that way, but that just other employee or oh, general, okay. General was 7. I like that, Ray. That works out. Yeah, I think enums is going to work out easiest for us here. All right, so we've got our queue here then, and now we're going to say for int minute is 0, minute is less than 120, minute plus plus. This will be our loop. So we said we have a 1/3 chance of someone showing up here in our time loop, sure. So we need a random number here, so random equal to new random. And then if random dot next, oops, I got to import random first, thank you. Random dot next int given a bound, next int given a bound of 3, if that equals 0, right? So given a bound of 3, we're going to get 0, 1, and 2. So 0 then is the 1/3 chance here. So q dot add, we're going to add a new person. But you need to give person a type. Oh, okay, so if we want maybe we do a random type instead. How do we do that? Maybe we don't need to tell you the type. Maybe we pick a type here for you. So we'll need a random generator for person then. Yeah, we can do that. Why don't we do that? So random equals a new random. Random, and then we could do a switch, I guess, or we could just do an if else. I don't know. Switch off of I don't like switches, so we'll just do that. So we'll have a int for type equals random dot next int given 3, and if that's ugly. No, I don't want type. This is value, sure. If value is equal to 0. We'll say type equals nurse. Type.nurse? Is it type.nurse? There we go. Else if value is equal to 1, type equals type.doctor. Else type equals type.other. There we go. Yeah, it wants me to replace. Why would I replace with a switch? I don't want to replace with a switch. I don't like switches. Here we go. So we can just add a new person. And that will randomly generate that type of person here. So that's my 1/3 chance. So we can possibly add a new person to the queue. Okay? Then if queue.is empty, nope, is empty. If it's not empty, take that, Nintendo. Huh? I missed it. Sorry, Dusty. Oh, that I don't want to switch. Yeah, I got you. No, I actually like our Switch. We play some good games on it. I'm a fan of that. We don't have the PlayStation or the Xbox, unfortunately, but we do have the Switch. The kids got into Animal Farm with their cousins. They had a lot of fun, and then the grandma got her own Switch, so she could play with the cousins. And she got really into it and collecting acorns and stuff. Like, her island is actually much cooler than ours. So they like to go hang out at her island. All right, so if the queue is not empty, then we need to go serve somebody. Oh, in person, that's right. So we need to track person the time they entered the line. That's right. So we need sets and gets for these. So let's go add some code. Right, I don't want to write it here. Let's let NetBeans do the work for us here. So let's insert some gets. Of course, we need gets here. And let's insert some sets. Insert some set code. Setters. There we go. All right. We can insert some sets and gets. So we'll make the person, and then we'll say, oh, bummer. We need to tell them when they entered the line. We can't do that with that. All right, so we're going to have person, new person, lowercase p, person equal to new person. There we go. Add the person, and person.setTime. Entered the line is going to be the minute. Then we can add them to the queue. There we go. If they're there, great. Now we can go do something with it. Oh no, this needs to be inside of our loop here. So if there's someone there, then we need to take their order. So possibly add somebody. Oh, sorry. Then if there's someone there, let's go take their order. So we need to get their order and figure out how long it was going to take for them. So we said that was just random 0 to 5 toppings, right? Topping 0 to 5. So 1 minute plus the minute per topping. Okay, so let's go take their order. So if the queue is not empty, I guess we could do it this way. I don't know. This is, we need to serve them, and then we need to wait to see if someone's being served. So maybe we have a Boolean for, is someone being, or I don't know, is someone's sandwich being made? Starts off as false. Okay, so if someone's sandwich is being made, we don't care. So if there's not someone's sandwich is being made, and the queue dot is empty, why does it do that? Is empty. So if we're not making someone a sandwich, and the queue's not empty, then we can take the next customer, right? So then we'll make someone a sandwich. We'll say this becomes true. Right, we're going to make someone a sandwich, and then we'll take the person off the queue. Queue dot. There we go. Let's remove, right? No, we don't want to. What? Are we a priority queue? What just happened here? Aren't we a priority queue? Q dot peak. Shouldn't be able to remove. What's going on here? Why is our priority queue funky? Yeah, this Java one is looking weird. Why is this letting us do this? What's wrong with the Java API? API priority queue. Priority queue. The head of the queue. The least element, yeah. So how do we get the item there? That's really weird. Sorry, folks. This doesn't look like the usual one. That's really screwy. Okay, sure. So we'll peek. So person next in line, I don't know, next equals q.peak, sure. And then we can remove them, right? So q.remove next, sure. And then their sandwich will be done in random next minutes. So int number of toppings equals random.next int, and we said next int said 0 to 5, so 6 will give me 0 to 5 here. So then the next dot set time order was received. No, my goodness. Set time order was received is going to be the minutes plus 1 plus number of toppings. Minutes? Oh, minute. So we'll get their topping, right? Oh my goodness. So we need a time that order is going to be done. So an int for time order is completed. Starts off at 0. We can say if minute equals time order is completed, then is someone's sandwich being made? It's false because we're done. So time time order is completed will be minute plus number of toppings plus 1. There we go. So then we can just set it to that. I like that. Set it to time the order was completed, right? We'll say, hey, whatever time it is now, plus 1, plus the number of toppings is when it will be done. That's the time their order was received. So we'll know what time they got in line, and then we'll know what time their order was done. Great. Yeah, that ought to do it. Right, we'll take them off the queue. I think this will work because it's getting their memory address, so this should work even without a equals here. This should remove the person that we added for their type. And we should just keep on looping then. I think that ought to do it. But now we need to track how long that took, right, for each person. Oh my goodness. So we need a total time, right? So an int total time for nurse. Ugh, that's ugly. Sure, int total time for doctor, 0, and int total time for other, 0. Ugh, okay, sure. So when we grab them off the queue, we'll say if next dot get type equals employee person dot type. Oh my goodness. Type dot doctor and nurse. Person dot type dot nurse. Then the total time for that should be what? Nurses, doctors, others? Others? I don't know. They're all plural, sure. Total time plus equals. That's going to be the time the order was completed minus the time they got in. Oh, that's okay. So next dot get time order was received minus the next.get time entered the line. Hey, how you doing, Marsafe? Hope you're doing well. Right, that ought to do it there. So that'll add to the total time for nurses. We don't know how many total nurses there were. Oh my goodness. So then we need an int for number of nurses served. Starts off at 0. Number of doctors served and number of others served. Doctors. Others served. All right. Oh my goodness. And number of nurses served plus plus. Goodness. Okay. Else if the type is doctor. We need a better way to track all this, folks. This is ugly here. Total time for doctors and number of doctors served plus plus. If you're not a nurse, you're not a doctor, you're else then, right? So just our else case. You must be an other. Total time for others and number of others served. Yeah, we're talking about priority queues. We're using a priority queue here for this project. We're going to have a little fun with it. Try to see if we can simulate this line. What do you mean it wasn't used? Total time for nurses. Yeah, I used it right here. Plus equals total time for doctors. All right, I think my suggestions are just confused. We're totally doing that. Those here. Okay, so if we're not making a sandwich, great. So if we got to the point where the time order was completed, good. Then we can say, all right, we're not making someone a sandwich. We'll get the next person out of the queue, and we'll start making their sandwich. It will take that long to make them. We're just assuming it will get done. We don't, like, at the 120 minutes, we close the door. We're not serving new people. We'll finish whoever was there. Everyone else in line gets turned away. Bummer. That's bad for you. All right, but we're not, like, displaying any information here. So maybe we should display some information. That might be helpful. Do not add person. So maybe we need a way to, like, display what the type is. So why don't we add a toString? Override for public string toString. We'll return, how about type dot name? How about name? Get the name of the ordinal. So just random person. It just displays their type. People don't have names, they just have roles, right? This is they're full-time equivalents, right? We don't treat them as people, they're just full-time equivalents because this hospital only cares about making money. This hospital cafeteria, right? And the hospital only care about making money. So we just treat people as full-time equivalents, not as actual human beings who have lives and other things that are important, right? Sure. So we'll print out new person entered, new FTE, right? E entered the line. That's full-time equivalent. So that even, like, we don't even treat part-time employees as people. They're the partial full-time equivalents. Ugh, whatever. Line plus person. We should get their toString here. So, okay, new person to the line. And then we completed the sandwich here. So we completed sandwich for, how about we define next up here, or maybe we'll make this as like being served. How about that? We refactor rename. This is being served. Person being served, sure. For being served, so we need to define being served above here. Okay, so we'll get being served. Uh-oh, might not have been initialized. Okay, sure. So we'll start them off as null. That'll be ugly, but maybe it'll be okay. So we completed the sandwich for somebody, and then here we'll start making their sandwich. So we get them out of the queue, right? So making sandwich for. So how about we say started making sandwich for plus person plus at plus minute. Sure, why not? Oh no, sorry, that was being served. We need to do that right here. So we grab them, remove them, say we're making the sandwich for them, and then complete a sandwich for being served at plus minute. So we will say that, okay, we completed their sandwich at this minute here. Awesome. We started making the sandwich, we completed making the sandwich, new person entered the line. Sure, that ought to work. When all of that is done then, right, when our loop is done, our for loop is done here, right, we can say, right, cafe closed after 120 minutes. We can print out some averages. So we'll say average average time from entering line to getting sandwich for nurses. And now I'm going to feel a little bad about this because this is going to be the same code more than once, but we'll fix that in a second here. For nurse was, this will be the total time for nurses divided by number of nurses served. But we want that as an average. We probably want that as a double, right? So one of these should be a double, right? Otherwise we're going to get integer division. And integer division can be ugly here. So how about we do, one of these should be doubles. How about total time is doubles there? We'll just make total time be doubles. Okay? That way we get a double result. Sure. All right. We're going to do the same thing 3 times. That's fine. For doctors, that's total time for doctors divided by number of doctors served. We could make this into a method, but that's okay. I'm not feeling too bad about it. Nurses, doctors, others, total time for others, divided by number of others served here. That ought to tell us, then, how long people waited. Right? Right, we'll see how many people, I don't know, we could even see, like, number of doctors served. Oh, why not? Number of nurses served plus number of nurses served. I like that, sure. All right, now I'm feeling bad. We got the same code in here a bunch, but that's okay. Doctors, number of doctors served, number of others served, number of others served. Look at that. All right, let's see what it does. It might work, might not. Hey, look at that. We served some sandwiches. Uh-oh. Do we never... What happened to all of our prints here? We never did those prints at the end. Something, okay, I think this is my project, my properties here get screwed up. So this compiling setting is wrong. I need to undo that. Now it ought to actually compile when I run and give me the latest version. This looks happier. Yeah, stuff is happening. All right, here we go. So we served 16 nurses. It took them 5.87 minutes to get a sandwich, which is pretty good, given that it takes a minute plus the number of toppings to get someone's sandwich done. We served 11 doctors. They took on average 12 minutes, and we served 5 other people. It took them 21 minutes to get their sandwich. By the time they waited for doctors and nurses to get through the line, got their toppings. Okay. You know, maybe if we just added a second worker making sandwiches, this whole thing could be a lot faster. Right? And we could calculate that sort of thing by adding more people. We could do that sort of thing, but we don't like have the sandwich worker concept here where the sandwich worker takes the order and makes it. But we could do that sort of thing, I'm sure. All right, let's run it again, see what we get. Because it's all random, right? It's 6.8, 7.2, 13. Okay, this was a little better here now. Total people served. 18 plus 13, so 20, 31. We made 31 sandwiches in 2 hours. Oh man, we're a slow restaurant. We should see how many people like we kicked out of the restaurant we didn't serve. Right? Maybe we'll do that. So it's out my queue dot. Do I not have the queue here? Where's the queue? I have a queue. Yeah. Queue dot. There we go. We have a size, number of people were not served, right? Plus number of people were not served because we just closed. We'll see how many people were left waiting. Just curious. Because we should get about 40 people in line, right? So we left 3 people hanging. We served 30 people. Okay, so we only got 33 total out of the 120. Okay, so not close to the, not exactly 40, but somewhat close. It's not going to be perfect because it's random. It should be random, right? Sometimes more, sometimes less. So now we have 11 people not served, but we did serve 33 people again. Okay, so 33 plus 11, we had, ooh, that's pretty good. So 43, so more than the average, right? 6.6 minutes for a nurse, 9.6 minutes for a doctor, only 5 minutes for other, because only one other person ever showed up in the line, or at least they got served. Maybe a lot of those other people never got served. That's probably what happened here. Right? We spent most of our time serving nurses and doctors. We didn't get to those other people. And the one person who got through, because they got lucky in line, only took 5 minutes. Everyone else waited, was never served. So again, our average number here is probably a little off, but that's essentially what was happening. Does that make sense? Kind of how we tackled this, again, just using the priority queue with a class that is comparable here. Just similar to what you folks had for Project 4. I think that meets all of our objectives here then, right? Sorry, I have a bit of a cold. We ran for 120 minutes. See the average wait time for each worker type. Once we get the sandwiches done, we move to the queue, get the next person's order. We were taking their order first, sure. Otherwise, weird things would happen. Like you'd start someone's sandwich and just put it behind. Maybe that happens. I don't know. Using our time loop, a third chance a new worker enters the queue with a random worker, right? That look kind of what you had? Yeah. Okay, we're similar. And it's gonna, because it's random here, it's what it is. We'd have to run the simulator multiple times to kind of average out the averages. Because each time we run it, we get different results. Excuse me. All right, so let me commit that to GitHub here. All right, come on, there we go. So let's load 2353. And we'll commit those. There's Project 4. So you can see priority queues are pretty cool, depending on what we need to do, right? That when we add them, they upheap themselves to the correct location, or they downheap themselves. Right? We remove somebody. When we add a new person, we add them to the end, and then they upheap to the correct location. Now what's interesting is that our queue is actually, we should probably actually also compare the time waiting, right, to make sure that that's happening properly. Because what could happen, right, if we get a bunch of nurses in line, right, the way that the queue is done, as they start upheaping themselves, as soon as they find another nurse, they're going to be done, and we're going to take the ones from, usually, right, if we have 2 nurses, right, there's no other way to compare them, so it probably would be best then to also compare the time waited. Yeah, we should probably do that. I like that. So if they're the same, then we should compare. Yeah, we should do that. Okay, so we'll do that. So I'm not sure it's going to impact our numbers much, but it could, in that the way that we're grabbing people is just by nurse or by doctor and everyone else. So we want to make sure that if there's 2 nurses, we're going to compare their waiting time to take the one that's been waiting the longest. I mean, whoever got there first, we want to maintain that order, and we're not doing that currently. So why don't we do that? I think we can do that. So we can say if the type.ordinal equals the other.type.ordinal, or really just other type matches here, right? If the type matches the other type. If they're the same, then we're going to return my time entered line minus the other time entered the line. So if we have the same type, see, if I entered before they did, will be negative, right? So if I entered at minute 2 and they entered at minute 5, 2 minus 5 is negative, then I'm going to be less than, I'll go up to the front, right? Does that make sense? So this will make sure that the person who's been waiting the longest, who is there first, will be served, will compare to less than, so they'll bubble up to the top first. Because that's important when we start using our priority queues and our comparisons as we do the upheaping process, right? And we start picking the smallest next child, the smallest child when we do our swaps, when we downheap, right? Make sure they downheap correctly. This might help our times here a little bit. Maybe. Well, let's see. I don't know if we'll get too many different results. So we had 6.6, 9.6. Let's run our project again. Yeah, 6 and 7. And again, you know, kind of depends on what we had, but I think our numbers will be a little bit better this way. Yeah, 4 and 6. 15 other people. Wow, we did pretty good serving people here. I think this made a decent difference. 3, 7, 14. Okay, yeah. Other people are going to wait a while because they have to wait for everyone else. Yeah, I like that. I like that. So when we have a total people served, right? Total people served is equal to the number of nurses served plus the number of doctors served plus the number of other people served. Number of people not served. Oh, I don't know. Maybe we change that. So that should be what? Total people turned away or not served. Not served. Queue size. I like that. All right. And then we can have the actual details. So I don't know if we needed all this other like actually happening here, but we could do that just for fun. This is just sort of tracking what's happening. Right, so like we had, all right, a doctor entered a line, and then nurse entered a line, and then a doctor entered a line. Let's see, how many people do we have in line? Total. Doctor entered a line, nurse entered a line, as we're making someone's sandwich. We finished the doctor's sandwich, now we start making the sandwich for the nurse. 2 doctors got in line. We finished the sandwich for the nurse. We started for the doctor. More doctor got in line. Nurse got in line, so the nurse should be next. We start making for the nurse at 31 minutes. Doctor got in line. Yeah, so this looks pretty good, I think. Seems to be happening, right? Total people... Oh, I did the wrong one here. Total... What? What just happened here? Number of nurses served, number of doctors served, number of others served. That's not right. What? Oh... Okay, this is, we had 16 nurses served, 17 doctors served, 1 other served. We forgot our order of operations, folks. That'll guarantee now we get arithmetic, not string concatenation every time. That's going to be a little better here. There we go. 31 people served, 6 people not served. 6 nurses, 4 minutes, 7 minutes for doctors, 7.6. Hey, we did pretty good here, right? Waiting 7 minutes for a Subway sandwich? Not terrible, right? I mean, not fast food, but not terrible speed. We got pretty lucky there. 5 minutes, 13 minutes. Oh man, we had a lot of nurses we took care of. Doctors had to wait a while. My other people. This is skewed because we turned away probably 15 other people, I'm assuming. So, you know, again, the average is a little funky here because all these other people just waited and never got their sandwich. But, you know, that's our cafe. All right, so this is ensuring, I like that. So this ensures people of the same type, or it ensures of the same type who waited the longest go first. We can compare their time they entered the line. All right, I think we had enough fun with this project. Does that make sense? We feeling okay with it? Other questions, thoughts, concerns? We ready to move on to new stuff? Oh, we don't need that. remove some junk. There we go. Move some junk. Imports. My autocomplete sometimes is, I select too fast and it picks the wrong thing because I'm impatient. Alright, we okay so far? Alright, it's quiet. It's quiet. Maybe quiet's a good sign. You should actually see how many people are like around. Quiet's usually, I don't know, it's hard to see if you're nodding or not. Maybe we should go back to Zoom and I should make everyone turn on their webcams, because that is awful. Just chat at me here. We got a decent number of people in chat, right? A couple people hanging out in chat at least. All right, just vibing. I like it. Good vibes. All right, good. Glad you're feeling good. Again, I'm assuming you did your self-assessment fairly and properly, so we'll assume that your score, unless something really funky happened. But I think we should be in pretty good shape otherwise. Oh, what happened here? The time order is completed. We should set that off at like -1, because we were getting those funny prints here. Right, I got a funny print. All right, I don't need to keep fixing this up, but that's okay. Right, completed the standard for null. That shouldn't happen. Okay. That'll at least prevent that if we make that -1. Right, and then people enter the line. Oh, we should also print the time, I guess. FT into the line. Yes. At last minute. All right, I said I would stop. I just need to leave it alone. This is print prettier. All right, we got to leave it alone now. Okay, now I want to do like stick figures. All right, we need to move to new stuff. Let's talk about new stuff. So searching, there's not actually really anything interesting to do in code when it comes to searching, because we've done basic searching, right, where we start at the beginning and we look until we find something, possibly going all the way through the end. So for an unsorted list, right, if I just have a bunch of numbers here, or a bunch of things here in my list, right, it could be anything, whatever we're having a collection of, right, we look at the first one and we see, is it or not? Is the next one it or not? Is the next one it or not? Is the next one it or not? Check. As soon as we find the one, we're done, right? We found that item, whatever it happens to be, in my collection. So in terms of best case, right? Best case, which again is really silly. Most of the time we don't care about best case, is O of 1. The best case is it's the first thing. I did one comparison out of n items. Sure, we don't really care. That's a sad face, best case. Because how often is it going to be the very first thing you look at is the one you wanted? Probably not very often, so we don't care. On average, it's somewhere in the middle, right, is the average. Maybe it's the first, maybe it's the last. So when we average out first and last, it's middle. Middle of n, half of n, is still O of n, right? We don't care about the half. The half gets thrown away thanks to the magic of math hand-waving, right? We care about n operations, because half of n is still slow when you have million things, right? It's really the n is what drives how fast that is. Now, half of n is better than 2 times n, sure, but again, we throw away those coefficients most of the time for a hand waving. And our worst case is still O of n. I looked at n items and I didn't find it. It wasn't there. So like really this is, half is average and, 1 the full amount of n, but we don't really care. So on average it takes n operations to find something in a list. In a collection. This is a collection. Here. Right? Could be a list. Could be sorted, sorted we'll get to in a second. That's a little easier, but just some sort of collection, whether or not it's a list or not, takes n operations. Now, if we're in sorted order, right, this gets to be a little bit nicer here. So if I'm in sorted order, let's say we're going to find a bunch of numbers. So just throw out a bunch of numbers. I'll throw them in sorted order if we can help it, and then we'll see if we can find one of those numbers, and we'll see how many operations it takes. Because there's a trick to doing this, to making searching sorted collections faster. So a sorted collection here, we're going to see is going to be faster. I don't know if I've just got lag or what's going on, but you folks aren't giving me random numbers, so I'll just come up with a couple. How about like 7 and 13 and 19? Oh, you had 13. All right, right, thanks. How about 24 and 42 and 60? That should be a 0. I guess it doesn't matter if it's 66 or not. 60 and 91. So here's some numbers, right? They're in sorted order. So what we can do, when you ask if there's a number in my list, I'm going to start in the middle here, right? Just like our number guessing game. When I say guess a number 1 to 100, you're going to guess in the middle. You're going to guess 50. And I'm going to tell you too high or too low. And now, just by knowing too high or too low, you've eliminated half of the options. So if I go guess a number, let's guess 50. And I go to the middle and I say, okay, are you higher or lower than 50? Or are you 50? If this is less than the number, if I'm guessing 50 here, I know that it's not any of those. I've taken out half of my numbers. So now I can look at the next half, find the middle, and say, are you 50? No. Okay, well, I've taken out half of those numbers. You're less than. I'm going to go here now. Are you 50? No, you're not. Okay, well, you don't have 50. I can't find 50 in the list. It's no good. It's gone. But it took 3 operations out of an n of 7. Right? It took 3 guesses, 3 checks out of 7. 3 out of 7 total numbers to see whether or not you had that number in a sorted collection. We did not have 50. So at most, it's going to take, I think, 3 checks every time for n operations, for 7 items. 3. So what we're going to get here, as n gets bigger and bigger and bigger, every time we're going to do half and half and half, right? So if my n is bigger, right? If our n was, say, if we had 12 items, right? The first guess will knock out 6 of them. Either it's there or I've eliminated 6. So in one guess here, one check in the middle, I'm down to 6. And one more check, I'm down to 3. And one more check, right? Either I found it or it's greater than or less than. I'm essentially down to 1 item to check. So really that's 4 checks. Because we're halving it each time. Because what's happening, right? We're taking half each time. The fancy term for this is a binary search. Right? It's either there, too high, or too low. Right? We're guessing, taking the middle, and we're going to go to the low end, the high end, or we found it. That's a binary search. You can only do that in a sorted collection. Right? If my collection is sorted already, then I start in the middle, and I either found it, or it's higher, I take the higher end, or it's lower, I take the lower end. Each time you're cutting off half of the items. Actually, really half plus 1 because it wasn't that middle one, which is nice. Right, so it's half rounded down, essentially. Each time, so when I had 7, right, what I'm left with then, right, if I had 7 items and I guessed the middle, I'm going to take half of that, it's 3.5, and I'm going to floor, I'm going to round down, means I have 3 left. So then 3, that's divided by 2, right, 3 divided by 2 is 1.5. Floor, that is 1, and I just check that last item. Is it that 1 item or not? 1 divided by 2, floored is 0. When I'm at 0, I'm done. When I had 12 items, right, we said 12 divided by 2. So 12 divided by 2 is 6. Floored is still 6. Sure. 6 divided by 2 is 3. Floored is still 3. 3 divided by 2 is 1.5. Floor that. 1 item left. 1 item, 1 divided by 2 floored is 0.5. Rounded down is 0. We're done. So what we get here is this logarithmic growth. So a binary search, still best case is 1. It's the first thing. It's the middle item. Again, we don't really care, but on average, right, we're going to find it in some number of those halvings. Whether or not it was all of the halvings we didn't have it, some of the halvings, right? So when we have things, it's a log of n. And again, that's worst case is log of n. log of n here. Appreciate we're talking about binary search as we search through a sorted collection. So if we have a sorted collection, we can do a binary search. I should write that better, I'm sorry. This is a binary search. Binary search. C-A-R-C-H, a binary search. So a binary search gives me logarithmic performance if we're sorted. Again, it all depends on being sorted, but if we're sorted, we can do this cool halving search where we throw away half each time. And the book goes through, you can read through the text if you're curious. You can do this iteratively, or you can do it recursively. The recursive portion is just a loop. So iterative versus recursive, they're essentially the same to write. It's not too big of a deal to write it here. But we could write our own. And let's do that. Let's write our own here. So we start a new project. Oops, I don't want to undo. That was wrong. So we'll start a new project. We'll call this searching. So we're going to write a method here for public static void. This is a int here. We'll give you the index at which it was found, or -1 if not found, right? Remember when we try and find something, we'll give you the index or -1. We'll call this search, or binary search, right? We'll do, so public static int, this is regular search, or unsorted search, right? Unsorted search. Right? You can search some sort of collection here, right? This could be, again, there's all sorts of cool generic things we can do with this. I'm not too concerned about the generic syntax here. So let's just do an unsorted search of an integer array. Sure. This is values here. Again, we could make this generic, right? It could work for any type that is comparable. Right, okay, sure, we'll do the comparable. So this is a collection of type T where T implements comparable of T or something like that. This some funky looking T syntax. Oh goodness. Well, all right, I've got to go. Let me check my notes here and see exactly what we need to do to write it. I'm sorry. Okay, so where is it here? Sorry. I'll find it. What do we get here? His snippets are so terrible. I'm not a fan of how he writes his code. Okay, there we go. So this is a static. Okay, this is T extends comparable. There we go, comparable as long as something is comparable with the super type of T. We can give you, there we go, the collection of T. All right, we'll just do an array of T. That's easier, sure. T array values. Okay, so if T extends comparable, it is comparable of at least the super type T. So you might subclass it here, perfectly fine. That's okay. We'll do an unsorted search of T values, as long as T is comparable. Right, T values, we're going to unsorted search values for the T item. We're going to look for item in the values, or I don't know, we'll call that collection, I guess, sure. The collection of T, we're going to look for T item. So this one's really boring. Right, we're going to say for index is 0, index is less than the collection dot length, because that's an array, right? Index plus plus. And we'll say if the collection, if the item dot compare to the collection at index. If that equals 0, then we're going to return the index. If we've gotten through the entire loop and we haven't found it yet, oh, sorry, compared to, I'm missing a wrong direction here. If compared to that equals 0, there we go. If I compare it, the item, to the current index that I'm at, if that's 0, I'll return the index. I found it. Right? I compared, it's equivalent, we'll return that index. If we go through the entire loop, we haven't found it, we'll return a -1. This is the unsorted search, right? This is O of n on average, right? Average case. Average performance, average O of n, sure. Right, best case, it's the first thing at index 0, we're done, we found it. Great, sure. Our sorted search then, or our binary search, right? This will be our sorted search. So if T is sorted, again, you have to have T sorted already. Right? I'm not going to sort it for you. I'm going to assume it's already sorted here because you did a sorted search. We're not going to start at 0. Right? We're not going to do that. Right? What we're going to do is we're going to have an int for beginning, starts at 0, and an int start index is 0, and an end index is going to be the collection dot length -1. Right? That's the last valid index. So I'll have a middle index is going to be the end index, really just divided by 2, right? Because, sure, I don't know. Or we could end minus the start index is really the proper portion here. That's our middle index. Right, and what we're going to do is we're going to move the start and end to find, right, either this half or this half in our sorted search. So we're going to check the middle index first. So we're going to say if the collections at middle index dot compare to collection at middle index dot compare to the item, or maybe that's backwards. Sorry, if the item compared to the collection at the middle index, there we go, equals 0, we found it. We're going to return the index, or the middle index. If it's not that, right, well, now we need to see else if. All right, so I guess we should store that. So we'll have an int for result, or the comparison result, sure. Comparison result, is that 2 S's in comparison? I don't know. Comparison. I'm terrible at this, I'm sorry. Is the compare to. So now if my comparison result is equal to 0, I found it. Else if the comparison result is less than 0, I'm not sure, Mishi. We'll see how long it takes. Kind of depends. Where's my closing curly brace? Where's my closing curly brace? There it is. What is going on here? Oh, I got too many of them. Goodness. Closing curly brace. I guess we're returning that, else is redundant at that point. Illegal start of type. If, oh, I never started my curly brace. There we go. Started my curly brace and the curly brace. If, all right, return -1 if we don't find it here. Okay, if it's less than, well, now we need to move the start and end. So if it's less than, the start should stay the same, and the end index should become the middle index -1. Right, and we're just going to keep on doing this here, right? We're going to keep on looping here while the start index is less than the end index. We want to keep on doing this thing. So as long as our start is less than the end, find the middle, compare it. If it matches, return the middle. Otherwise, if it's less than, it must be less than, right? It's at the left half, and now moves to the left of middle. If it's not equal and it's not less than, it must be greater than the start index moves to the middle plus 1. And we just keep on going over and over and over. If we find it, great, we return it. Otherwise, if we've gone all the way and now our end moves past the start, or the start moves past the end, either way, right? Once they've crossed, right, it's no good. If they're equal, well, actually, if they're equal, that's okay. If they're less than or equal to, that's fine, because maybe we're at the very last item here, right? When we look at this operation here, so with our numbers, let's try and find something that exists. How about with you 13? Let's search these numbers for 13. So 7. So we're gonna let me take out. Can I take out those X's? I don't know if I can unmove those X's. Can I grab them and move them? Move that X, right? There. Okay, I moved the X. Remove that X. There we go. Move that parenthesis and that X. Remove that. No, I just want that one small one. I don't know how to get the one small one. That's fine. So we're going to search this for 13. We're going to say, okay, well, start is 0, end is 6, because my index is 6. So the middle is 3. So this is index 3, right? 0, 1, 2, 3, 4, 5, and 6. So the middle index is 3. Check 3. Is it greater than or less than? 13 is less than, so it'll compare to less than. So now my end will move from 6 to the middle minus 1. The end will move to 2. So now I have started at 0, end was 6, now end changes to 2. So now the middle is 2 minus 0 divided by 2. Right? My middle's 1. I'm going to check the middle index is 1. I found it. We win. We get the index. That sort of makes sense what we're doing with our... And this is the iterative version rather than the recursive. I think the iterative is actually easier than the recursive version. The book disagrees, but that's fine. Sure. Doesn't matter. Right? Are we okay with this? Can we move start and end until we've overlapped? So we should see if it works, right? So why don't we try it? So we'll make a integer array, values equals a new int array, and let's just give it some values, right? We had, what do we have here? We had 7, 13, 19, 7, 13, 19, 19, 24, 42, 24, 42, 60, 91. We'd say I don't know, what do we look for first? We said 50 is at index plus the sorted search values, and we want to define 50. Sure. Oh goodness. Is it not? T is not comparable. Is it an integer array? Is that better? Integer array. Okay. Use the type here because the type is comparable. The primitive is not. Sure. So we'll find 50 should be -1, right? And then we said 13 should be at 1, right? That one should work. If we find a 13, and then if we find a, I don't know, let's look for, say, 91. Should be an index 6. Using our sorted search. Oh, we got to change the properties, sorry, so that it compiles. All right, let's see. Does it compile? Uh-oh. Is it actually running? Am I stuck? Uh-oh. Might be in an infinite loop. We did something wrong here. Still running. Let's see what we did. We want the sorted search, right? So let's see what happens. Put a breakpoint in, run it with debug mode, see what we broke. Oh, I think it's my equals end index here. That must be the problem. Oh, it should be okay. I don't know. Let's find out. We'll see. So we're going to try and find, here's our collection, right? Here's our numbers here. We're going to try and find 50. So start is 0, right? End is 6. Life is good. As long as they're less than, yet we're good. My middle index, then, is going to be end minus start divided by 2. So the middle's at 3. Good. Let's compare. My comparison result is positive. So it means it's greater. It's in the greater half, right? Which we expected, because 50 should be at the right-hand side of 24. So my start should move up to 4, right? So start moves to 4, which is good. All right, we're going to check. 4 is less than or equal to 6, right? Good. Middle, compute a new middle. The new middle, well, that's not right. Oh, that's right. Okay, so this is wrong when we compute the middle. So start minus end divided by 2. The middle of 4 and 6. That should be that plus that. It should be plus divided by 2. Not minus, right? I can't figure out an average. Plus the end plus the beginning divided by 2 will give me the average. That's the middle. That ought to do it. Okay, that was a nice little bug. My mistake there. There, okay, now it runs, right? Index 1, index 3, and this should work whether or not we do the sorted search or the unsorted search. Sorry about that, folks. An unsorted search should work the same way, but remember, performance is different. Again, it works super fast for this, but this was not as fun. So let's fix this up. Let's do, how do we write a method here? How do we write a static void test unsorted search on size n. Or I don't know, we'll set test searches on size n, given int n, or size, I don't know. Okay, so if you give me a size, then we'll test it here. So we'll make random equals a new random. And then for a given size, so we'll make an integer array of values equals a new integer array of size. Right, and then, we got to import random. So let's add a bunch of random numbers for index, I don't know, number is 0, number is less than size, number plus plus. Let's add a random number to values. Oh no, goodness, we want, because we want it in sorted order. Let's just add the sorted numbers. How about that? So we don't even need random right now. We'll do that after. We'll take values at, how about index? Let's fix this as index. Values at index equals index. We'll just throw all the indexes in. So it'll be 0 through size. Sure. Then we want to find a random number inside of it. There we go. So then we want to find a random number up to that. So here's the int random number equals random.next given size, right? That'll give me 0 up to, but including size. Next int, sorry, size, and then the random number is at index, and we'll use the unsorted search values and the random number. And then we'll use the sorted search to see how fast it is. We'll try. Okay, so we'll say searching for random number. Okay, unsorted first, sorted first. All right, now let's try it. So we'll do a bunch of big ones here. So let's test search on, let's do about 1,000, and then do 10,000, and 100,000, and 1,000,000. We can throw in our underscores here for fun once we get so big. 1,000,000. Let's do 10 million. 100 million. We'll try 1 billion for fun too. How about 1 billion? All right, those are all ins. After that, we're going to run out of space. Let's see how well that works for us here. Relatively okay. Oh, it's still okay. It's still even finding. Look at that. It's running. What is it doing now? What's it doing next? It's not telling us it's searching for anything. Uh-oh, out of memory. Oh, goodness, we ran out of memory. Oh, I guess I can't put 1 billion integers into memory. Oops. My bad. For out of size values. All right, so the billion was no good. Sorry, ran out of space. We should be able to do 100 million though. I think I have room for 100 million. So that was 10 million. 100 million, okay. That went pretty quick. Well, it wasn't showing us that the sorted search was that much faster. Okay, if I do the sorted search first, maybe we'll see how much faster that is. Just trying to catch it here. It's slower. Slowest part is adding the numbers. That's a bummer. You saw it took a little bit of time. Okay, that wasn't super interesting, but this one is faster, doing the sorted search. Logarithmic is much faster than linear of n. Yeah. Not super interesting. I'm sorry, folks. Didn't demonstrate that as well, that this was super fast. The sorted search is much faster. We saw a little bit of delay, but not much. But that's okay. The sorted search is fast. That's the whole idea. All right. Cool. We haven't taken a break yet, have we? Oh my goodness. We are only into searching. We still need to talk about... Come on back. Where'd it go? Dictionaries and hashing. We can spend a little bit of time on hashing next week if we need to. We could still have to talk about the final project. When we take a break, we'll come back and talk about dictionaries. And then we'll talk about the final project. Maybe we'll leave hashing for next week. We'll see. Got a little bit of time still, but not too much time. Trees and binary search, yeah. Well, let's do dictionaries and then the final project, and we'll talk about hashing next week. Okay? That sounds like a good plan? So when we take 10, put the music back on, we'll pick it back up in 10 minutes. We can go from there, okay? Hey folks, how's everybody doing? So we got a quick break in there. All right, I'm realizing it's running a little late already. I don't want to go too heavy in any given night, so I'm thinking we can actually leave dictionaries and hashing for next week, and then the week after, because we already really talked about heaps, we can jump right into trees, binary search trees, balanced search trees the week after, and then we might do a little bit on graphs on 811 then, depending on how long that takes to cover. Because we had to spend some time talking about Project 4. It kind of ate in a little bit of that time. So I want to get to the final project tonight, so we've got time to talk about it and start doing some planning, some working on it there. And I think it'll go all right. I think that'll be fine. So we'll talk about the final project tonight. We'll leave dictionaries and hashing for next week. Maybe start talking about trees, get to binary search trees, balanced search trees, maybe graphs, and then see if anything needs to fall into 811. We're not going to do anything with graphs for the final project, so that should be okay. That sound okay? So I want to make sure we leave time for practice and to think about some of these things, and you can try some of the exercises in the text and work through some of it. It's unfortunate not having lab time when our classes are really designed to, here's a topic, and then we'll go play with it in class after. That play with it exercise is a little trickier to do remotely. So let's talk about the final project. Does that sound okay? All right, so we're going to pull up assignments here. Bring up a final project here. All right, so again, this one is due on 8/18. We meet at 6 p.m. to gather together for this. This is our final project. Make a new final project grade here, and this one is 40 points total. We'll work on a rubric a little bit later here. So I'll give you a link for the GitHub Classroom. Here we go. Grab that link here in a second. Here's the final project link in pairs or even a trio, you want to tackle the extra objectives required. Right, so if you do work in a trio, you'll have extra work to do. For pairs or individually, it's the same project. Please submit the feedback, pull request URL, and a self-assessment to the rubric. All right. Okay, so I need to spend a little bit of time talking about some things. Yeah, we can talk about the extra objectives in a little bit. We'll talk about the main project first, and then we can get to the extra objectives. Yeah, I'll put those. I'll do like a separate rubric for that, because if I add them to the main rubric, it screws up how the scoring works for the other ones. So I'll just list them out here in like the project description for the extra stuff there, if that makes sense. All right, because I'm assuming like we've got a month to do this sort of thing, that we'll just get everything done, and that's sort of the goal, is that in the group we get everything done. Okay, cool. I like that, Professor Burp. Thanks. Yeah, that's a good question, because trying even like adding bonus points to a rubric, it's really obnoxious in D2L. I've yet to find a good way to do that. Maybe I just need to ask better questions, but the tools as I see them don't seem to work as well as I'd like them to work for bonus points. All right, so we're going to have a little bit of fun. We're going to do some simulations here. And part of what we're going to do is use this Monte Carlo method of doing some simulations, because we're not going to be able to do all millions and millions and millions of simulations to get the actual result. Hayes, that's a good question. I don't typically offer extra credit, but I kind of like that idea. If your duo wants to, or even individually want to grab those extra objectives. Yeah, we can think about that. But at that point then, if the trio says, well, they want a chance at extra credit, then I need to come up with like even more above and beyond stuff for the trio to do, and that spirals a little bit awkwardly, but that's okay. You know, I can be open to that. Yeah, if you want to try that, I think we can do that. That sounds fun. All right, so the Monte Carlo method, again, is this idea that when we run simulations, if we can't actually simulate every single possibility, what we're going to do is we're going to take a random sample of the possible results of the possibilities and simulate those to generate, okay, well, if there were 10 million possibilities that could happen, let's take 10,000 of them and simulate. And we'll use that 10,000 simulations to say this is probably the odds of the all 10 million here. We're going to use a portion of them. Now, the problem is, right, we need to make sure we're picking from the proper distribution. And if you haven't had a lot of stats, don't worry too much about it here. I'm going to give you some cliff notes here that are probably close enough. Some of my math friends might object to this, but that's okay. So what happens here is, if I'm going to tell you we're going to pick a number from 0 to 1,000,000, then the odds of you getting a number between 1 and 1,000,000, if these are just perfectly random here, are 1 in 1,000,000, right? I think that makes sense. If you say 1 out of 1,000,000 here is your chance of getting a number between 0 and 1,000,000. Because they're just a random distribution here, right? They're numbers. No big deal here, right? It's 1 in 1,000,000. That's what your chances are. That's what your odds are of picking one of those. Right now, but for something that's not completely random in even distribution here, like a lot of times you might see these sort of bell curves where most of the numbers then fall into these groupings, right? So with a bell curve, if you look at, hey, like what's the average height of a person? right? So if we say, oh, where's my screen here? This one. So average height of a man. The average height of a man, sure, depending on your country, sure. Just give me something here. 5'10". 5'9". Okay, so sure. So we'll say the average height here then. So average represents the center here is 5'10". Average. Sure. Let's look at, I think it's going to give me a nice little graph here too, right? Going to give me the nice graph? No. Average height and, okay, so I want distribution. Distribution of height of a man. Yeah, this looks probably pretty close. Again, it's not exactly right. We're just kind of looking for it here. Sure. Why am I 5'10"? That's not even, where's my graph? I had a nice graph here. There we go. So what you get is this sort of graph here in which people are close to the average. So the average here, why do I have two lines? Why is red and one must be, okay, it must be female. It's probably 5'4" and male is 5'10". Okay, so the blue graph for men, right? The average is right up here. You're kind of tall if you're at 6'1.5" or so, looks like. Right? And you're kind of short if you're at the 5'6" or so mark here. Right? You're very tall if you're at the 6'3"-ish above, and you're very short if you're at the 5'3"-ish and below. This idea that we have this distribution of the values happening where most of the people are in the center, right? The average here, where we get more of a grouping. So if you were to say, okay, well, the possible range here, we have people who are as short as even like 4'8", right? And people who are as tall as, 7 feet. And we got a couple basketball players in the world and a couple of people who hit 7. But most of the people fall into the range of this middle section. So in the distribution, right, we said, what, 5'6" and 6'2" or so, we're going to get most of the population in here, and then you can go further out and you can get less people in these other 5'2" range and maybe 6'6" range. So if I were to say, pick a height for somebody, and you just say, oh, give me a random value between 5'2" and 6'6", a random value is not a proper random pick because the distribution is in such that you get more people in this range. Does that make sense? Kind of what I'm going at? So I can't just say pick a random number between 5'2" and 6'6" and say that that's a good random sampling. So with the Monte Carlo simulation, we need to make sure we're getting the proper distribution of random values. Right? All of that hand waving to say we're going to make sure we pick the right randoms. Hey, Jack. Are you back?
Me?
I can't pick you up right now, buddy. I got to finish teaching. I'll pick you up after. Okay, can I pick you up? Oh, did you bring me my hat?
What?
Here, you brought me my hat? One second. Here. You can bring up my hat for me. I'll take that.
No, please.
Yeah. I have to finish teaching, though, and then I can go back. Yeah. Pick up the hat. Pick it up downstairs to Mama.
No.
Yeah, we got to go back to Mama.
No, please.
Sorry, folks. I think I left the baby gate open on the stairs. Hey, is this hat going to work here? Jack brought the hat for me. Oh, I got to change hats already. Ready to Professor Burp. I'll let you folks decide. Mickey Mouse hat, Chessbrot hat. Oh, I had the other one. I'll go grab the other one for you, just for fun. All right, I still don't have the white one from last semester, but I do have this one I'll offer you. Came off of one of my kids' dolls when we went to Amish country. So we can try that if that's all right with you folks. Is that fair? Doesn't quite fit. I mean, it's doll shaped, but maybe that'll be fun. The small hat. All right. So the Monte Carlo distribution. Now, we're not going to actually have to worry too much about this in what we're simulating, but I want you to be aware that it only works if we're picking the proper random values at the distribution in which they should be sampled. Does that make a whole lot of sense? So if you pick 100,000 people, 100,000 men, right, you're not going to have 1% of them at 5'2", 1% of them at 5'3", 1% at 5'4", or whatever that, like, you know, that's 12, 14 different. So you're not going to have 14% at each height distribution. You're not going to have 14% at 5'2", 14% at 5'3". It doesn't work like that, right? That's no good. Okay? Because of this distribution curve. All right. Thankfully for us, though, we're going to just be dealing with random numbers, essentially, random values. We're looking at that. We'll have just, they're uniformly distributed. Perfectly fine. We can just pick 10,000 different possibilities here, and that's the exact same possibility as 10,000 other ones. So this works for us because we're going to have this uniform distribution. We don't have some sort of curved standard distribution here like that. We're just going to have a uniform distribution. All right. Anyway, all that fun here. So we're going to use a Monte Carlo simulation to give odds of winning at Texas Hold'em. So Texas Hold'em is a card game here. Oh my goodness, my hat fell off. In which you play poker. It's a poker variant. Here, so let me grab the Wikipedia page is halfway decent. Texas Hold'em. Here we go. For Texas Hold'em. So the way Texas Hold'em works is that you get 2 cards. All of the opponents, however many ex-opponents you're playing against, each get 2 cards. And then there are rounds in Texas Hold'em in which cards are dealt into a shared pile. So there's betting that happens before when people just have 2 cards. Then what happens is there's a flop. A flop happens when you get 3 face-up community cards. So 3 cards are played into the middle of the table, and then anybody can use a combination of their cards and the community cards to make their best 5-card poker hand. Okay, more betting happens. Then another card, or the turn, is dealt. A 4th card is dealt into the center. 4 community cards, plus your 2 shared cards. Okay, so out of those 6 cards, you make your best possible 5-card poker hand. I can find out which way is on the screen here. So with 6 possibilities here, you pick a combination of 5. So there are 6 ways in which you can make a 5-card poker hand at that point. So 6 combination 5. Remember, combination, not permutation, because it doesn't matter if your first card is an ace or your second card is an ace. As long as you have an ace in there, you'll have that ace in your 5-card poker hand. So the order doesn't matter. So we're dealing with combinations. Then another round of betting, and then a 7th card is dealt. A 5th card is dealt into the community cards, along with your 2 shared cards. So now there are 7 possible cards that we're going to grab in combination of 5. So you could use all 5 community cards and none of yours to make your best possible 5-card poker hand. You could use 2 of yours and 3 of theirs. You could use 1 of yours and 4 of theirs, right? Any way you want to do that. So 7 combination 5, you're going to get 21 possible 5-card poker hands. That one of them is the best possible poker hand. Okay? So that's the Texas Hold'em hand. Right? So what we're going to do is for each round, pre-flop, turn, or pre-flop, flop, turn, river. So the pre-flop is 0 community cards. Flop is 3 community cards. Turn is 4 community cards. And river is 5 community cards. We're going to calculate the odds of winning by using a Monte Carlo simulation to get 1% of the possible community cards, community card combinations. And the 990 possible opponent hands. So when we have all 5 community cards in play, and we have 2 cards, that means there are 7 cards taken out of the deck that we know of. So with a deck of 52 cards, that leaves 45 cards left. With 45 cards left in combination 2 at a time, our opponent could have 990 possible hands. So we only know what our 2 cards are this entire time, right? At the pre-flop, when there are no community cards, right, that means there are 50 cards left. So out of 50 cards in combination 5, right? So when we know no community cards, there are 5 possible cards that can be put into the community card pool out of the 50 possible. There are 2,118,760 possible community card combinations of the 5 community cards that could be played, right, into the middle. So we only want 1% of those. So we want to do, right, 1% of that should be 20,000, 21,000 or so, right? Cut off 2 zeros, 21,000. I think that's right. 21187. Yeah, 21,000. So there's 21,000 possible community cards combinations we could get, right? Once we know what those 5 community cards are, then our opponent could have 990 possible opponent hands. We don't want to do all of those either, because 21,000 times 990 is really big. That's going to be a lot of possibilities. So we're just going to pick 1% of their possible hands to kind of narrow this down as we go. Right? We want to be around 100,000 simulations or so each time. So we can generate the odds of winning if we know, okay, here's 21,000 possible hands, community card combinations, and we'll just say maybe like 10 possible opponent hands. We'll figure out what our odds of winning are, because we're going to compare our cards to their cards. Okay? We're going to do it again for the flop. When we know what 3 community cards are, we need to generate, well, there's 2 more possible community cards, right? If we know what our 2 and the 3 community cards are, that's 5. Thanks, Dusty. I'm glad you like the hat. So 5 out of the 52 leaves 47 left, and we need to pick 2 more community cards. So at that point, there's only 1,081 possible additional community cards. That's not so bad then, right? That we can get. But out of those possibility community cards, there's still 990 possible opponent hands. It does rival it, you're right, than the floppy white. I gotta find that floppy white flower one still. Right? When we know what 4 of the community cards are, there's 1 possible card left out of the remaining ones we could add to the community cards. Once we know what all 5 are, it gets a little easier. So kind of what's happening at each of these levels is we're getting less possibilities as we go, because we know we have more certainties. So our opponent's 990 possible hands are always uncertain. We don't have no idea what they are. Right? There'll always be 990 possible opponent hands once we know what the 5 community cards are. But the 5 community cards, we get lots of options, slightly less options, much less options each time for the community cards. Right? So for pre-flop out of 50 cards, there are, what do we say here for that? That was 50 C5, 50 combination 5. I copy that, 2118. 760, Here we go. Possible 5 community card combinations. So at the flop, out of 47 cards remaining, there are, so given 3 that we know with 47C2, right, there's only 1,081 additional community card combinations. 1,000, what did I say? 81 possible 5 community card combinations. So that's not quite so bad, because we know what 3 of them are. The turn, so out of 46 cards remaining, there are only 46 possible 5 community card combinations, right? Because there's only 46 cards left in the deck, community, and we know what 4 of them are. So if we know what 4 are, and there's 46 cards left, there's 46 possible 5 card combinations for the community cards. In the river, we have all 5 community cards. There are 990 possible 2-card opponent hands. And this is for in a 1v1 game. Okay, this is the 1 versus 1 game. When there's additional opponents, the math for winning is still how often does my hand win against any possible opponent, but whether or not an opponent is still in the game changes a couple things. It's not too, don't worry too much about it here. Okay, so obviously we can't do 2 million times 990 possible. I mean, we could. It's just going to take a really long time. So for every possible community card combination, if we calculated the 990 remaining ones, we're doing almost 2 billion operations there. That's going to be a lot of operations to figure out the odds for pre-flop. It's not so bad once we get to the flop and the turn, and it's easy once we get to the river to do the 990. Right? That's not hard at all. Okay. Dusty. So this is what we're going to be doing. Does that make sense? So the good news is, I've got the Hold'em hand class and the poker hand class done for you. I'm not too worried about those. Okay? The goal is how we're doing these simulations and how we're going to be storing this data in a way that's very accessible and performant. And how are we going to say, this is how fast it should run? Yeah, so I've got those out here for you. So we actually did that in 2151 this summer. We did a basic Texas Hold'em game for Project 2. So I've got a Hold'em hand class that is comparable to another Hold'em hand. Right, so it has 2 cards, and then it has a list of shared cards that you can add to it here. Right, and then we can get the best possible poker hand out of that, given the 5 shared cards. Right, so you have to have 5 shared cards to get the best possible poker hand, but it will take all 7 possible cards, right, add them together, generate all possible poker hands, and then find the best possible poker hand, the 5-card poker hand, out. Excuse me. Okay, so I've got these ones out here for you. So the Hold'em hand and poker hand classes are done, and I think they work. They should be fine. I think someone found one bug, and I think I fixed it back when we did this. So the logic there for the game itself is already there, right? The Hold'em hand, poker hand, logic. So what we're doing is we're writing, well, how do we figure out what the odds are here in a 1v1 game. Right? So at each round, then, how do we display the odds? Okay, before there are any community cards, what are my odds of winning just knowing my 2 cards? Well, that's a lot of possible. That's like 2 billion possible things could happen, right? We're going to do the Monte Carlo simulation, say, let's do like 1% of the community cards and maybe 1% of the possible opponent hands to start. We don't want to do too many. Once we have less, we can do a little bit better, right? We don't need to do just 1%, right? And if you say, if there's only 990 possibilities and you take 1% of them, the odds are crap, right? You want to do all 990, right? But when we're at slightly higher, we can do less calculations each time. Okay? So we're going to display the odds of winning, drawing, and losing at each betting round. We have more than like 10,000 possibilities. These or so. So like at about 10,000 or so, it's not too bad to do, and you'll be able to see how fast it runs. It shouldn't be too bad or so. Okay, and we're going to use the odds of winning. Have the computer player bet, call, or fold. So when we bet, call, or fold, right, then it's up to the computer, this 1v1, we're going to play against the computer to pick an option. Does that make sense? So I think let's do this. So if you are in a trio, use the odds of winning. For pairs, individuals, or pairs, the computer will just always call. The computer will never fold. We'll do that. Okay, so if you're in the trio, you're actually going to use the actual odds. So computer should raise or call if their odds of winning are greater than or equal to 50%. Right? Otherwise, the computer will just always call. Right. I'm going to work on a rubric in a little bit for you folks. We'll get through some of the specifics in a little bit. I don't want to take too much more time tonight, but that's the general idea of it. Right, so we'll have the rounds, we'll have them be able to bet, and we'll display, hey, this is your chance of winning based on these are what your 2 cards are, whether or not we know any community cards or not. And we can go each time. Okay. What do you folks think? So I got that out there. Again, we got a month to work on this here. Right? Please don't leave this for the last week. Things will go badly. Right? I can about guarantee things will go badly if you leave it for the last week. That's why we've got a month to work on it. We don't need to get it all done. So you're going to show your game when we do the final presentations, and you'll show that it shows the odds at each round of betting. So you'll say, hey, let's play the game here. So here's the one-on-one game. I get 2 cards. It shows me what my 2 cards are. Here's the odds of winning. Maybe a little bit of behind the scenes, like this is how many possible combinations, or some kind of fun stuff maybe. Or we can just look at your code and see like where it's doing the generation. Right, but we got the logic here for here's what a hold'em hand is given 2 cards. So we can generate the possible 990 hold'em hands that my opponent can have if I know what's left in the deck. Right, so here's a deck of cards. Right, we'll go grab cards out, just removes a random card out of the deck. Oh, no, okay, so it shuffled it, it just removes the last card. Sure. No GUI. Because not everyone has taken Java 2 or 2151, and not everyone who took 1500 even did Java FX GUI stuff, which makes me really sad. Yeah, so you can use this hold'em logic here for poker hand, for hold'em hand, for the deck, and for cards as starter code. what we're doing here is we're focusing on, well, how do I do the simulations? How do I store all this information in memory? What data structures am I going to use to find all this sort of thing? Because there's a couple cool ways of doing it, right? When we generate possible hold'em hands and poker hands and winnable hands and combinations and things like that. There's some fun things we can do. And then we'll talk about performance as well, right? Analyze some of the complexity when it comes to space complexity, right? How much am I storing in memory? And time complexity, how much time is it taking in terms of N operations to do these sorts of things? So we're going to have to kind of talk about our decisions and what data structures we're using and how they perform as well. We'll do some of that analysis as we go. Yeah, tonight went by real quick. Or the whole course itself went by quick. Is that what you're saying? It's been 11 weeks. We only have 2 more weeks of content, essentially. And we'll have gone through, was that 29 chapters in the text? So there's a lot of stuff when it comes to data structures, looking at how we store data in memory. Yeah, 29 chapters of text. So a lot of stuff. It's been a lot of fun. Sorry I'm behind on getting stuff scored for you. Apologize. We got an extra week on the midterm if you need it. Let me know if you need to resubmit. The 0 will come up automatically. Don't worry about that. I'll fix that as we get these things scored. But I had to do that so you could see the quizzes as I'm working through finishing those up. Okay, so we're going to leave dictionaries and hashing for next week. I think we can get through dictionaries, hashing, maybe some basic trees, and then binary search trees, balanced search trees, and graphs the week after. And we should be good to go. Okay. Yeah, it's been fun. It's been a little while since I've taught the data structures course, a couple of years. This is one of my favorite courses because data structures are so interesting. And looking at how we store data and why we do it the way we do is really interesting. Just in terms of this is how things happen behind the scenes. Yeah, there's no quiz on hashing. I don't think I'm doing a quiz on searching. That's just not really enough to talk about. It's like unsorted searching and sorted searching and binary searches. That's it. That's all we did. Like it'd be 3 questions. Not very interesting. But once we've covered a little bit more, maybe we can pick up another quiz. Okay. All right, folks. It's been fun. I'll leave you with some time to digest, to think about it, play with it a little bit. Got another hour and a half or so to do that. I do have office hours tonight, starting at 10 to 11. Gonna drop on by. Again, we can book individual appointments outside of the regular office hours if needed. I try not to do things on weekends if I can help it, because I'm busy doing other things. So, yeah. All right, folks, you take care. Let me know what I can do to help. Again, the goal is that you folks finish the final project 100% successfully, and everybody gets it working and done and gets some experience playing with some of these data structures and analyzing them and being able to discuss in an intelligent way why we made the choices we did in terms of time complexity and space complexity. Because when it comes to programmer interviews, right, those are the sorts of questions you're going to get asked. And some companies do a really bad job at it, some do a really good job at it. What we look for is, can someone intelligently discuss these things? Do you have enough knowledge to say, hey, I can do the analysis and I can talk about it, and I can defend my choices and say, this is why I went this route, because I think this is best for this reason quantitatively, right? I can quantify my space performance, I can quantify my time performance, and I can say it is best for these reasons. And we might not be right all the time, and that's okay, right? And someone else might have a different idea. But unless we can quantify it and we can say this is how it performs in time and this is how it performs in space, right? CPU time and memory space, or disk storage space even sometimes, right? Until I can quantify those, we can't even have that discussion of which is better and why one is better. That's what we need to understand. Right? And that's why we study these things, because it is important. It's more than just, hey, this performs XYZ, memorize this table, or go look up this table every time, right? Unless we have gone through and kind of studied and engineered, designed them, written them, it's much harder to talk about and to understand. Okay, so that's sort of the why. All right, folks, it's been fun. Let's see. I think Lantern Noir's on Twitch. I don't know which other friends are on, unless you folks have anybody you're interested in rating. We'll call it a night. And we'll go for it. Office hours are just time to meet and chat. Talk about questions you might have. Look at projects. That's the one-on-one time I have to work with you folks. Lantern Noir is playing Red Dead Redemption. Boyd is doing some resin pours. Okay, that's pretty fun. We got some chess happening over at St. Louis Chess Club. Rob is on doing some more tech stuff. I don't know exactly what. Just says think and chill. Neuro's playing World of Warcraft. If you want to go watch some World of Warcraft. Dr. WD-40 is online, trying his new outdoor setup, which is fun. The Chess Bros are playing chess. Gonna head over that way maybe. We haven't been there in a while. Maybe we'll do that for fun. See if we can raid their channel. I don't know if anybody's allowed to raid them. Yeah, alright, we can do that. Alright, folks, it's been fun. You take care. Let me know what I can do to help. Again, the goal is you folks get this done and are able to talk about it. You take care. See you around.